So, after last night, I got an email from Anthony. Thank you for your email, Anthony. Expressing that the entire class needed help on this last assignment. Needless to say, I haven't received work from every person in the class regarding integration. I also haven't heard from every single person in the class that you needed help on integration. So please, please, please reach out to me with any questions, comments, concerns. Come to my chats. Send me emails. Send me a G chat. It's in the bottom left-hand corner of your email. A couple of you guys are just now starting to find that. That's a very easy way to get in contact with me. I do have that on my phone. Text me, call me, ask me for questions. Do not just say, I need help on this. Tell me what it is that you need help on, okay? So tell me what it is that you need help on. Come with specific questions. So what I did was I made a little PowerPoint with all of the rules. I'm going to dub over all of the rules. We're going to talk about them a little bit. I have some examples. These are not easy. The same way you guys thought that derivatives were really, really hard when you first started them. This is going to seem really hard now that you're first starting this. But once we get all the rules down, it should be a lot easier. The same way derivatives got really easy, this can get really easy. So you have 4 basic rules, and then you get into some generalized rules. So you have the integral of a constant is the constant times the variable that is in the differential. So if the differential is x, it will be k times x. If this was dt, that would be k times t plus c, where c is that constant of integration. That is always going to be there. The reason why is because in the realm of parent functions is if we have a plus c, its derivative is 0, which will not affect the integral when we have an indefinite integral. Okay. The next is the constant multiple rule. So you have k times a function is going to be equal to k times the integral of that function alone. That basically says that you can factor the k out. You can factor that k out. Okay, and then this is the sum rule, which is the integral of 2 functions being added together under the same differential is equal to the sum of their integrals, and the same with the difference. Okay, so these are what they are called. Okay. Now, a lot of you guys, the same way with the derivative rules, the derivatives have a sum and a difference rule as well. You guys understand that polynomial functions have operators between them. So the addition and subtraction pieces here, we can separate polynomial functions into individual pieces that allow us to evaluate, allow us to take different derivatives, etc. So power rule. So the power rule for integration was designed to be the inverse operation for the chain rule. So the reason why these look like this is because chain rules have derivatives within them. So the simple power rule is the integral of x to the nth power with respect to x is equal to x to the n plus 1 power over n plus 1, always with the plus c. Now this works for every number, every variable that is not -1. That is because when you have x to -1, its integral is the natural log. So you have to just remember that's a special case that we'll get into on the other slide. Now the general power rules with the U substitution, this is saying that x is not just a single variable. This can be x as a function, etc. And this is saying that if the function is present and its derivative is present inside of the integral, then we can use U substitution in order to get this new integral statement. So we have u to the n with respect to u. The integral of that is u to the n plus 1 over n plus 1 plus c. Now remember, this is a fraction. Like this n plus 1, that divisor, that denominator, is actually a constant. So I could write this as 1 over n plus 1 if I'd like, which you might see on another slide. Okay, so you have exponent and log integrals that you got introduced to last week. You have simple and general forms of both. The integral of e to the x dx is itself is e to the x plus c. That mirrors the fact that its derivative is also itself. Now, general exponent rule, you have e to the u with and then you have du over dx with respect to x. This actually cancels out. So you have a dx and an x here. So that actually neutralizes. And that gives you this second statement, e to the u du. This is assuming that u is another function. So like, for example, it could be 2x plus 1 or like x squared plus 2x. That would mean that this du here has to have this whole exponent's derivative present. And you'll see that in another slide. Okay? And then you have simple log rule and the general log rule. So if you have 1 over x dx, the integral of that is the natural log of the absolute value of x. We have to put that, the absolute value of x in an absolute value sign because we don't know if the function within it is always going to be positive. If we know that the function is always going to be positive, then we don't have to write the absolute value sign. For example, if you had ln of x squared, like x squared is always positive, so you don't have to write that. But we need to be able to evaluate it, which is why we have that absolute value sign. Okay? And then the general logarithmic rule is 1 over u du dx dx. The integral of that is 1 over u du. This is stating that the u, that amount that's in that denominator, that is not just x. It could be a function. So like, for example, 2x plus 1 or x squared plus x. That would mean that its derivative, that denominator's derivative, needs to be present within the integrand. So, for example, if I had 1 over, if I had like 1 over 2x, that means that I would have to have a 2 dx here in order for me to use this rule. Okay? Now, I could make a 2 dx, like if I didn't have it here, that means I could put a 1/2 outside to neutralize it, which we will go into in another slide as well. Okay, we could have a bunch of different things, but the idea here is the same general idea that I got you guys into the habit of thinking when we were doing derivatives. Sometimes you need to use more than one rule, so you really need to do a good job of diagnosing what is going on within the problem. Okay, so we need to rewrite sometimes. So for example, if you have a negative exponent, it's always really good to rewrite. If you have a square root sign, it's always really good to rewrite. Remember, the square root is a half exponent, so that's really good. So what I said before, identify what you have, diagnose your problem, figure out what rules to use, make the appropriate substitutions, perform the rules, substitute back your substitutions. Now, these are only if you need them. Okay, that's why I have them as like 3.1 and 3.2. Sometimes you need to make a use substitution. If you need to do it, do it. If you don't. That's fine. And then always identify your solution. So for example, this is the first rule. I have the integral of 4 dx. I'm diagnosing what I have. I have a constant and I have a differential. So that means if I have a constant and a differential, I'm using the constant rule. So I have the integral of 4 dx is equal to 4x plus c. Now, I'm always going to check my work. I'm going to check and make sure that this side, if I take its derivative, I should get this inside, okay? So I got derivative of 4x is 4 with respect to x, which is what I have, and then the derivative of a constant is 0, so I keep going. Beautiful, okay? Now, here's another example. So this is an example that I would have to rewrite. First thing I'm going to do, I'm going to diagnose my problem. My integrand has an exponent in the denominator and a differential. An exponent in the denominator means I have a negative exponent. So I need to rewrite, and I use a simple power rule. I'm going to rewrite this, okay? So now this is in a form that's for my simple power rule. I can use it if I'm doing a direct plug-in. So I do -3 plus 1, -3 plus 1. That gives me -2. So now I see I could leave it in this form if I wanted to. I could leave this as x to the -2 over -2. That's fine. I wrote it like this. I brought out the 1/2. So -1/2 x to the -2 plus c. Now I'm always going to check my work. -2 times -1/2 is +1, which is what I wanted. And then we're going to -1 in our exponent. And then we end up getting -3, which is exactly what I wanted. Okay. Now, here's one that would use a lot of rules. This uses a bunch of rules if you really wanted to think long and hard about that. So I have a constant times a squared variable. and I have a constant being added, and I have a differential. Okay, so that's what's going on in the problem. That means I need to use the constant multiple rule, the sum rule, the constant rule, and the simple power rule here. Okay, a lot of rules going on, but when we start doing them over and over, they start getting a lot easier. But what I'm going to do is I'm going to break them up rule by rule, and you'll see once you start doing a lot of these, how the patterns start to form. So, for example, here, I could split this up. I have 3x squared dx plus 1 dx. Okay? Ooh, it goes fast. Now, what I can do is I can pull out this 3 so I don't have to look at it, and now I can just focus on this that's going on here. Okay, and then I have here. Okay? Now, when I integrate, I get 1/3 x cubed. You could also write this as this over 3 if you would want, same thing. Okay, plus c. Okay, and then this is the same adding sign, so I'm just bringing this down. And then 1 times x, because this is my constant rule. Okay, now a lot of you guys are getting tricked if I don't write this 1 here. There's always a 1 there. That's actually one of your problems in the assignment. Okay, so now I have 1 times x plus c2. Now these are both c's. They're both constants. A constant plus a constant is a constant. I can put them together. Okay. Now this is my final answer. I have 3 times a third. The same thing that would happen if I wrote it in my general constant rule form. If I wrote this as like x squared plus right? So that's x. Same thing. It's the exact same thing. This is times a third, just writing it like that. And now I have 3 times a third is 1. I have x, and then I have c plus c is a constant. Okay? And if I take this derivative, I have 3x squared plus 1, which is what I want. Okay. Now, I have e to the x dx. These are very easy. These should go really quick. I have exponential function. I have a differential. I need to use a simple exponent rule because I don't have anything being plugged into the x here. It's just x. I have e to the x dx is equal to e to the x plus c. And that's it. Okay. Do another really easy one. I have 1 over x dx. Once you see this, you don't have to really do anything with it. This is a known law and a known rule. I have the derivative of ln of x and a differential. I need you guys know that this is the derivative of ln of x. So you need to make that connection. Okay, I need to use a simple log rule. Bang, there it is. Ta-da. Okay, I'm going to do 2 u substitution problems, one with an exponential and then one without. Sometimes you'll see a function and its derivative in some form present within the integrand, and this is when you implement some u substitution. I did 2 separate lessons, one on a general u substitution and then one with a constant, like adding a constant in and out. So I'm implementing both together so that way we can just use one streamlined method, which you've seen this outline in your work before. So I have this problem, which is very similar to what your assignment problem that was due yesterday. So the first thing you do is identify u and du. So I'm looking here. What is the derivative of the other? So I'll take the derivative of both. 4x squared, the derivative of that is 8x. Is that in my integrand? No, it's not. So it must be this one. The derivative of 4x squared is 12x squared. All right, I have an x squared in here, so that makes a little bit more sense. So 4x cubed is going to be my u, and then its derivative is 12x squared dx. So you always have to remember that dx, because the dx needs to go away when I'm doing the u substitution. We need to have only one variable when we're integrating. We don't know how to integrate with 2 variables yet. So just make sure that you have that dx there present. So the next thing you're going to do is identify a constant if you need it. So I have a 4x squared dx, okay? And I don't need 4x squared dx. I need 12x squared dx. So that means I need to put in a 3 1/3, okay? Me putting in a 3 1/3 into here, into the integrand, is not changing the value of the actual problem at all because it is a constant and its reciprocal. A constant and its reciprocal multiplied together is 1. So I'm not changing the value. I'm just changing the way it looks for my needs. Okay? And then I'm going to substitute u and du into the integral statement. Okay? So this is what it would look like. I know I have a 3 and a third inside. I'm going to organize it so that way it helps me out the way I look at it. So I'm going to put a third in. I have 4x cubed times 3 times 4x squared dx. Now, here what I'm doing is I'm putting these together. That's the 12x squared dx that I need, which is my du statement. Okay, this is du here. Okay, and then I have 4x cubed here, which is my u statement, which is what I said before. Okay, u. Now I do the direct substitution. I'm left with 1/3 times the integral of u times du. Okay, and then I integrate. So here, I'm going to erase this so that way we can look at it a little better. I have 1/3, which is this constant that's outside. So I'll underline this so you know that's the same. Okay. And then this is the simple derivative rule. Okay, so 1/2 u squared. If I took that derivative, it would just be u, which is what I want, plus c, always with the plus c. And what I'm going to do is I'm going to simplify that. I'm going to put that together. Okay, so 1/6 4x cubed squared plus c. Now, to check our work, this would be a doozy of a derivative, but you get, bring 2 up. So I would get 2/6. I would get 2/6 times the inside, so the 4x cubed, okay, times this derivative. So it would be 12x squared. Okay. Now, that doesn't really look like what I have up here, does it? It will in a second, right? So 2 times 12, okay? 2 times 12 is 24. 24 divided by 6 is 4. So I can get rid of that. 4, which is exactly what I wanted. Okay, last one. Okay, so for example, if I had something like this, identify the u and the du. So since this is an integral, we have the u in our exponent. So the u is going to be the 2x. Its derivative is 2 dx. So you identify the constant and the reciprocal needed. You have 6 in here. So 6 is your constant that you could move if you wanted. You could just move it so you could be next to the dx if it helps you to look at it. Okay, you have 6. You need 2. So that means you need to divide 6 by 3 to get 2. So you need to put a 3 and a 1/3 inside of your statement. Okay, so here I'm going to put a 3 in, and then I have the 2x, the e to the 2x. Then I put the 1/3 in, the 6, then the dx. I'm putting this together because this is going to end up being my du, and I'm putting this here because that's my u. Okay, I'm going to take the 3 out because I'm not using it. 6 divided by 3 is the 2 dx, which is exactly what I needed for my du. Du. Okay, and then here's my u. Okay, so I have e to the u, du, 3. And then I'm going to integrate. So I have 3 e to the u du is equal to e to the u plus c. Always multiply by that 3. So that 3 is actually going to be right out here. It's going to be right out here. Oops, I made a mistake, but I caught it. This is why we dump these things. Okay. Thank you guys so much. Make sure that you're contacting me for help. I really want to see you guys calling, texting, emailing, commenting, interacting with things. I really hope you guys are well. Please feel free to contact me with any questions, comments, concerns, issues. Thanks so much. Bye.